Hello everyone. Today we shall start with the static characteristics of measurement. We shall discuss about the static characteristics of measurement. So the question will be asked in this way: list and explain the static characteristics of measurement. Static characteristics of measurement system describes its performance when measuring a constant or slowly varying input. These characteristics are crucial for understanding the accuracy, precision, and reliability of the instrument in stable condition. The key static characteristics are. So before that we start with the key characteristics, first you need to know what do you mean by static characteristics. It describes its performance when measuring a constant or slowly varying input. If the input is slowly varying, it also measures. So there are few key characteristics. You have 5 key characteristics. We shall discuss one by one. The first one is accuracy. Accuracy means the degree of closeness of the measured value to the true value. We know what do you mean by accuracy. It is an exact value. So exact value, assume it is a pi, just an example, pi we know the value. So accuracy means if we get an exact value of that, then it is called as accuracy. It means that the degree of closeness of the measured value to the true value. Importance: it describes how correct the measures are, often expressed as a percentage of full scale reading. Accuracy is defined as the closeness with which the reading of the instrument approaches the true value. The true value is just impossible to determine experimentally. The true value of a quantity can be defined as the average of an infinite number of measured value when the average deviation due to the various contribution factors tends to 0. So as you know, first key characteristics is an accuracy. Just summary: degree of closeness to the true value. So next one is a error. Error are unavoidable in any measurement system. Attempts can be made to minimize them, but suitably designing the system by taking care of all sources of error plays an important role. So we all know that usually error occurs in the measurement. It is unavoidable, so we need to understand how it can be avoided, and we need to minimize it by taking suitable care of designing the system. In order to have an overall estimate of all the sources of error, understanding through evaluation of error is essential. Accuracy of any measurement system is measured in terms of error. So what do they say is, when the system is proper, it is the measurement is done properly. If it is very close to the true value, then error will be very less. If it is not close to the true value, then error is more. So an approximation of the true value obtained by sufficiently extended series of measurement, and also taking into account parameters and condition to which correction may be applied, we obtain what is called the measured value of the quantity. While it is never possible to measure the true or exact value of a quantity, and it is nearly always possible to give the best measured value. The static error is defined as a difference between the best measured value and the true value of the quantity. Absolute value of error does not indicate precisely the error of measurement. The quality of measurement is provided by the relative static error. So overall, what did we understand by this error? What can you write? Error is nothing but it is very unavoidable. And one more thing is, we can minimize it by taking care of a designing system we should design it in such a way that error is being minimized, or taking care of what kind of error might occur and how can we overcome that. All these things should be there before should be taken into a note before we design a system. So this is called as error. Next, let us look into the problem in the error. So the problem is a pressure indicator showed a reading as 79 into 10 to the power of 5 Pascal on a scale range of 0 to 100 into 10 to the power of 5 Pascal. But the true value was 78.5 into 10 to the power of 5 Pascal. Determine the static error, static correction and the relative static error. So we know the formula for the static error, that is a measured value minus of true value. So we know the measured value 79 into 10 to the power of 5 minus of 78.5 into 10 to the power of 5. So that is equal to 0.5 into 10 to the power of 5 pascals. So what do you mean by static correction? Static correction is equal to a minus of static error. So it can be written as the answer which we have got from the static error, that is from the measured minus true value, that is 0.5 10 to the power of 5. So static correction is equal to minus of 0.5 into 10 to the power of 5 Pascal. The relative static error is equal to error divided by true value. So error is 0.5 into 10 to the power of 5 divided by 78.5 into 10 to the power of 5. That is equal to 0.00638. So the values might change. You need to remember the formula of static error, static correction and relative static error. Next one is reproducibility. What do you mean by reproducibility? It represents the degree of closeness with which a given value of a quantity be repeatedly measured within a close range. Okay, the reproducibility is a measure of closeness with which a given input may be measured over and over again. An instrument with high reproducibility has zero or negligible drift. What do they saying here? We are repeatedly measuring the closeness such that we get into the close range, so that is called as reproducibility. What do you mean by drift? The last one. The drift causes the measurement results to vary for a given input quantity. It occurs due to wear and tear of parts. Hysteresis effect in metal changes in metal caused by contamination or other causes. Environmental factors, stray electric and magnetic field, thermal EMF changes in temperature and mechanical vibration, high mechanical stress in parts. Thus, drift is an undesirable quantity. It occurs very slowly. Drift can't be easily compensated but can be carefully guarded against by care, prevention, inspection, maintenance. It is a drift which causes a change in calibration of instrument. So what do you mean by drift here? What can you summarize here? So that thing, if you understand, you can write it by your own words. So drift causes the measurement results to vary for a given input. See, it is mainly due to the wear and tear of the parts. Okay, it might also be due to the environmental changes. It might also be due to the contamination. It is due to many purposes. So these things cause a drift in the drift. So it can be compensated by a proper maintenance, prevention against the environmental changes, and if it is so, you can calibrate your instrument in order to overcome the drift. So in the drift, the gradual change in the instrument output when input remains constant. So here the importance of the drift is reflects the stability of the instrument over a time. Zero drift. Change in instrument, zero reading over a time. Span drift. Change in instrument sensitivity over a time. Expression typically given as a percentage of full scale per unit time. Coming into a sensitivity. Sensitivity means the ratio of change in output to the change in input. It indicates how much the output will change in response to change in input. Typically expressed as unit of output per unit of input. So now let us discuss the formal definition what it is there in the textbook. So sensitivity means it is the ratio of magnitude of output to the input signal or response of measuring the system to the quantity being measured. For an instrument having a linear calibration curve, sensitivity is the slope of the calibration curve and is constant over the entire range of the instrument. If the calibration curve is non-linear, the sensitivity is different at different points. Being the slope of curve at various points, the sensitivity of instrument should be high. Thus, the range should not be high in comparison to value being measured. The scale factor is reverse sensitivity. So this is about the sensitivity. Let us look into the problem of the sensitivity now. So determine the sensitivity of a pressure gauge as a ratio of scale length to the pressure if the gauge has a radius of scale line as 100 mm and pressure of 0 to 50 pascals is displayed over an arc of 270. The gauge has linear calibration curve. So there are a few formulas for this. Full scale deflection, length of scale, sensitivity. Full scale deflection is equal to 270, that is equal to 3 pi by 2 radians. Length of scale 3 pi by 2 into 100. Sensitivity, scale length divided by. So here you need to know the formulas for the sensitivity, that is full scale deflection, length of scale, sensitivity. The full scale deflection is equal to 270 is equal to 3 pi by 2 radians. This length of scale is equal to 3 pi by 2 into 100. Sensitivity is equal to scale length by calibration pressure. So by just applying the values to this, you do get the value, that is 3 pi per pascal. What do you mean by, next we shall discuss about the dead zone. What do you mean by dead zone? The range of input value over which there is no change in output is called as dead zone. So importance, it reflects the sensitivity limits of the instrument, typically given as a percentage of full scale. So dead zone is the largest change in the input quantity for which noticeable change in output is observed from zero reading. So what do they say here? It is a large change in input quantity for which noticeable change in output we can observe from the zero reading. It may occur due to the friction in the instrument which does not allow pointer to move till sufficient driving force is developed to overcome the friction forces. The dead zone is caused by the backflash and hysteresis in the instrument. Dead zone in a pyrometer is 0.1% of span. The instrument is calibrated from 500 to 1000 centigrade. Determine the minimum temperature change for it to be detected. The span of instrument is equal to 1000 minus of 500, that is equal to 500 degrees centigrade. The dead zone is equal to 0.1 divided by 100 into 500, that is nothing but 0.5 degrees centigrade. So we have come across these let me quickly revise the static characteristics of measurement. Here we had discussed about the accuracy, error. In the error we had discussed about the problem, and then reproducibility and drift. Then we discussed about the sensitivity and dead zone. So these are the few static characteristics, and the static characteristics question will be asked for 10 marks. So where you need to explain all these things for in a paragraph. So the problem will be on the dead zone, sensitivity, and in the error. So these are the three problems which you need to remember. So in this class we will discuss about the dynamic characteristics of measurement. So the question will be asked in this way: list and explain the dynamic characteristics of measurement. So in the dynamic characteristics of measurement, you have two different types where you will in the dynamic characteristics of instrument, the dynamic behavior of the instrument is assessed by applying a known and predetermined input to the primary element and studying the resulting output such as movement of a pointer. So here what do we do is we will give some we need to understand if we give which kind of input, what is the output we can expect. We need to understand that, and then we need to conclude what are the output we do get. So here you can see the diagram. You can see the diagram that is a step change, linear change, and a sinusoidal change. In the step change, these are the kinds of input which we can give. So behavior is typically judged by using a 3 inputs. So you can see the step input. This is a line. This one is called as step input. Okay, the input changes instantaneously to a new value and then remains constant is called as step input. What do you mean by linear change? The input which changes linearly over a time. You can see there is a time here, so it is changing across as you go on increasing the time, it is also increasing. That is called as linear change. What do you mean by sinusoidal input? The input varies according to the sinusoidal function with a constant amplitude. So you can see here this is called as sinusoidal. These are the 3 inputs. By giving these inputs we will observe the output. So that is called as dynamic characteristics. Okay, let us look into it. Next, in the dynamic characteristics of instrument, it is there are few there are few characteristics according to the input how it has been varied. So these are the speed response, lag, fidelity, and dynamic error. You have 4 dynamic characteristics of an instrument in which the input, by giving few inputs, what will be the output will be evaluated in terms of. So coming into a speed response, so you need to write these 2 diagrams. So these 2 diagrams shows how the deadline lag depends upon the dead zone and the rate of which measured variable change. Looking at the first diagram, you can see the input what we have given here is a step change. Okay, in the x-axis and y-axis we have a time and an instrument reading. We also have a dead time lag here. So first let us discuss what is a speed response. It is a rapidity with which an instrument responds to the changes in the measured quantity. So instrument measured in the changes in the instrument responds to the changes in the measured quantity. What do you mean by lag? The delay in the response. So you can see this delay is called as lag. The lag, it is a delay in the response of an instrument to changes in the measurement type. Again you have a 2 different type, that is retardation type and delay time, time delay type. Time delay type is also called as dead time. We will also look into it. Next is a fidelity, the degree to which instrument accurately follows the change in the measured variable without introducing a dynamic error. So next you also have a dynamic error here. It is a difference between the true value that changes with the time, I mean the measured variable, and the instrument reading, assuming no static error. So here by looking at the diagram you can judge easily. So what do you mean by dynamic error or a fidelity in this? So look at here in the diagram. Here there is a lag, you can see a dead time. So then there is a measured variable and instrument reading. You have a dead zone here as well. So these are the two diagrams which you need to write. So let us look into the formal definition of all the four characteristics. What do you mean by speed response? The speed response is nothing but a rapidity with which an instrument responds to the changes in the measured quantity. The lag is a delay in which response of an instrument to changes in the measured quantity. Types: retardation type and delay time. Delay type. In the retardation, the response of the instrument begins immediately after a change in measured value but occurs at slow rate. Coming into a time delay type, that is also called as dead time. There is a delay before the instrument begins to respond, with the response simply shift along with the time scale. Generally, the dead time lag is very small. The instrument with significant dead time are unsuitable for measuring a rapidity fluctuating variable, and dead time can also be caused by finite dead zone in the instrument due to friction. In such cases, the instrument does not respond immediately and acts only when the measured variable changes sufficiently to overcome starting friction. The dead time due to this cause depends on how fast the measured variable is changing and extents of the instrument dead zone. Fidelity: the degree to which an instrument accurately follows the change in the measured variable without introducing dynamic error. It reflects how closely the instrument reading matches the true value of the measured variable. So dynamic error: the difference between the true value of a quantity that changes with time and the measured reading, assuming no static error, is called as dynamic error. The error indicates the instrument's accuracy in reflecting